Now let's see if we can find the limit at a vertical asymptote. So we've been looking at what does it look like, and we've been looking at where can we use our limits to find the vertical asymptote and the horizontal asymptote from a graph. So now let's see what we can do if we are given our equations like this. So we're looking at this one, and we have the limit as x approaches 4 from the right of 3 over x minus 4. And we need to see if we can figure out what this is going to look like. Well, let's go back to our Desmos graph for a minute and see if we can use that to help us out. So we're going to do our graph. So y equals 3 over x minus 4. There we go. And we're looking for the limit as we approach 4 from the right. So 4 is right here. So as we're approaching 4 from the right, it looks like this is going to lead us towards infinity. So our answer over here is going to be infinity. So we can agree that our answer is going to be infinity. So this is going to be a vertical asymptote. But the question becomes, how do we solve this without using our Desmos graph all the time? We won't always have access to the graph. So how could we figure this out? How could we solve this? Well, let's see if we can look at the denominator. See this denominator right here? We have our denominator right here of x minus 4. Where would x minus 4 equal 0? Let's find out. So x minus 4 equals 0. So x is going to equal 0 when x is 4. So let me try that again. The denominator is going to equal 0 when x is equal to 4. X minus 4 equals 0. So the denominator will be equal to 0 when x is equal to 4. That is your hint at where your vertical asymptotes are going to take place. So when we're looking at our vertical asymptotes, the limit at a vertical asymptote, the result is going to be infinity or negative infinity. But it's also going to have the denominator equaling 0. So that can be a good look at, oh, where should I have a potential vertical asymptote? Well, let me see where my denominator is going to be 0. And that can help you from there. So if we're looking at this one, another way to think about it is let's think about what happens. We have x is approaching 4 from the right. So x is approaching 4 from numbers that are bigger than 4. So like 5, for example, or 6 or 10 or whatever, something bigger than 4. So we're going to ultimately have a positive number divided by a positive number. And the denominator right here, depending on how close you get to 4, is going to be positive, but it's going to become smaller and smaller and smaller and smaller and smaller. So as you're looking at this, you have a positive 3 on the top. That's never going to change. Positive 3 will remain positive 3. But on the bottom, you have a positive number that is getting smaller and smaller and smaller and smaller. Well, what happens when you divide 3 by a very small positive number? Let's look and see. So here's just my calculator on the computer, just to show you. So let's say 3 divided by, and then a small number. So 4 from the right. So let's say we're coming up 4.5, for example. So let's divide 3 by, well, if we had 4.5 minus 4, that would give us 0.5. So let's divide 3 by 0.5. We get 6. All right, well, let's see what happens if we divide 3. Let's get even closer. Let's say that we're at 4.005. So let's divide 3 by 0.005. Look, 600. So as we keep getting closer, this value is going to rise and rise and rise. So we have a positive number divided by a very small positive number as we're approaching 4 from the right. And that is going to give us our infinity. Let's try again. So let's say that we have 3x, and now we are approaching 4 from the left. Let me put it over here. So we have 3x this time, and we are approaching 4 from the left. So we're going this way. So as we're approaching 4 from the left, here's 4. It looks like we're headed down towards negative infinity. Whoops. Oh, I didn't need this second box. There we go. So let's look at this one. Let's use our same logic. We know it's going to be negative infinity. Our denominator is going to be 0 when x is 4. So that tells us this has potential to be a vertical asymptote. Let's use I call it fuzzy math. Let's use a little bit of fuzzy math and see if we can figure out how this is going to happen. Now we are approaching 4 from numbers that are very close to 4. So here's 4, but coming from smaller than 4. So like 3.9 or 3.8 type numbers. So that means in the numerator, we're going to have a positive value. But in the denominator, a number smaller than 4 minus 4 is going to give us a negative value. But it's going to be a very small negative value. So we can say a small negative number. So that's what's going to give us our negative infinity. Over here, we had a small positive number. I notice I went to positive infinity. So how can we figure out the horizontal asymptotes? Well, this one was just asking us for the verticals, but could we figure out the horizontals as well? How about we finish the verticals and then we'll come back and talk about the horizontals. So for number 13, let's see if we can figure this one out. We have x is approaching -3 from the right. We have x plus 2 over x plus 3. So what can we do here? Well, first of all, where is our denominator going to be 0? So we have x plus 3 equals 0. So our denominator is going to be 0 when x is equal to -3. So we have potential for a vertical asymptote. So let's see what happens. So if I have -3 and I'm coming at -3 from the right, so that would look like, oops, let's try to draw a little straighter line. So here's -3. So 0 would be right here. So I'm coming at -3 from the right. So I'm going this way. So I have values that are very close to -3, but slightly larger than -3. So we'll have something that's close to -3, but slightly larger than -3 plus 2. So that's going to give us a negative in the numerator. In the denominator, we have something that's slightly larger than -3, and it's still negative though, but coming from the right towards -3, plus 3. So that's going to give us a positive. So it looks like we have a negative over a positive, so that's going to give us negative infinity. And let's look at the next one. So we have our limit as x approaches 3 from the right, and we're looking at the natural log of x to the second plus 9. Well, if you've ever looked at the natural log graph, I'll show it to you. Here we go. Let's bring our Desmos back up. So here's the natural log graph. Here's what it looks like. It approaches negative infinity when you are approaching 0. You cannot have the natural log of 0. And while it looks like it's approaching negative infinity here, you cannot actually take the natural log of 0. You cannot have the natural log of a negative number. And as you go this way, it's going to approach infinity. So as we would be approaching 3 from the right, so we're coming at 3 from the right, we know we can't have the negative, and we know we cannot have the natural log of 0. So let's see what our graph actually looks like so you can see it. There we go. So what we have to look at is this piece right here, this x squared minus 9. We cannot have that be 0 because we cannot have the natural log of 0. And we cannot have that be anything that's going to make it negative. So we can't have this value be any more than 3. So if you look at our graph right here, that is why when we're at the 3, we're noticing this curve right here. So approaching 3 like this, approaching 3 from the right, see how it's starting to curve. So when we're looking at our natural log as x is approaching 3 from the right, we're following this curve right here. So let's go back to our paper. So what we saw from our graph is our limit as x is approaching 3 from the right, of our natural log of x squared minus 9 looks like it's going to equal negative infinity. So there we go. So see if we can figure out some horizontal asymptotes. Well, when we're looking at horizontal asymptotes, we have a little bit of a cheat sheet that we can use. I'm going to show you that. So the limits at horizontal asymptotes go to, it means that you need to compare the numerator and the denominator. And when you compare, you're looking at the degree, and that means the exponent of the numerator and the denominator. If the degree of the numerator and the degree of the denominator are the same, then the limit is going to be the fraction of the coefficients of the numerator and the denominator. I'll show you what that means in just a second. If the numerator is less than the denominator, the limit will be 0. And if the numerator is greater than the denominator, the limit will be infinity. So let me see if I can explain this and show you what I mean. So let's look at this first one right here. We have the limit as x approaches infinity of 3x plus 5 over x minus 4. So the way you would go about solving this is you would divide everything through by the highest power of x. So that would look like 3x over x plus 5 over x all over x minus 4 over x, because our highest power of x is just x to the first. Well, then these x's would cancel, these would cancel. So you would be left with 3 plus 5 over x over 1 minus 4 over x. As x gets bigger and bigger and bigger and bigger, this is going to go to 0. So pretend you have 5 candy bars and you divide it into 1,000,000 pieces, you're basically getting nothing. Pretend you have 4 candy bars and you divide it into 1,000,000,000 pieces, you're basically getting nothing, is the idea. So these are both going to 0. And then you can see you're left with 3 over 1. Well, that is the technical way of going about solving this. Let me show you the shortcut. Look at your x's right here. See them? They are both to the first power. You have 3x to the first, you have x to the first. So that means that the degree of the numerator, the powers of the x's, is equal to the degree of the denominator. So that means that you can look at the coefficients. So 3, this is technically a 1 right here because there's nothing written. So technically a 1. So if we look at our coefficients, we have 3 over 1, which gives us 3. And notice that's the same thing that we had when we solved. So it's a little bit of a shortcut. Technically, what you're doing is dividing everything through by the highest power of x, like we did here in green. But you can use a little bit of a shortcut as well. So let's see if we can apply this to a couple different things. Let's look at this one over here. So number 16, we have x to the third in the numerator, and we have x to the third in the denominator. Now notice we also have x to the first and x to the second. That doesn't matter because we're comparing the degree, and the degree means the highest exponent. So even if they're in the wrong order or out of place, we need the degree, and the degree is our highest exponent. So if we do our comparison here, we would technically have a 1. So here is our highest exponent. So it looks like we would have 1/2. Let's look at number 17. Number 17, so here is our highest exponent in the numerator, it's x to the first. Our highest exponent in the denominator is x to the second. So this means that the degree of the numerator is less than the degree of the denominator. So this one will go to 0. Number 18 is a little tricky because we can't really see what the degree would be until we FOIL this out. All right, let's FOIL it out. So if we do some multiplying, we'll have 2x to the fourth minus x squared minus 4x squared plus 2. We don't really need to simplify it all. You could make it 4x to the fourth plus 5 in the numerator over 2x to the fourth minus 5x to the second plus 2. We can put our limit back in the front. But the moral of the story is now we can see our degree for our numerator and our denominator. We can see that degree, we know what it is. So we have x to the fourth in the numerator, and we have x to the fourth in the denominator. So the degree of the numerator is equal to the degree of the denominator. So that means the limit becomes the fraction. So 4 over 2, the numerator, the denominator, 4 over 2, which is equaling to 2. Let's try the next one, number 19. Well, now we have a problem. Just when we thought we were getting the hang of it, we don't have a numerator and a denominator. So now we're going to have to see if we can do some logic. So let's see if we have our limit here as x is approaching negative infinity. And we have, well, I see an x to the fourth in common. So let's see if we can pull that out. Let's see if that does us any good. There we go. Well, if I have our x to the fourth and I'm going towards negative infinity. So think about this, negative infinity to the fourth. And then we have 1 plus negative infinity. So this is going to give us a positive number because a negative raised to an even power is a positive. And if we're at negative infinity and we add 1, it's still going to stay pretty negative. So a positive times a negative looks like we're going to get negative infinity. Let's try number 20. What do we have here? Well, look at all these exponents. The highest exponent in the numerator is the fifth. The highest exponent in the denominator is the fourth. So it looks like these are our highest powers. So that means the degree of the numerator is greater than the degree of the denominator. So that's going to push it to infinity. Because the numerator is greater than the denominator, so the higher value is going to be in the numerator, and it's just going to keep getting larger and larger and larger. So we're pushing it towards infinity. When the degree of the numerator is less than the degree of the denominator, it means the highest power is in the denominator, and it's going to pull it down. We're going to be dividing by a large number. So that's like what we said up here. If we have 5 candy bars and we divide it into 1,000,000 pieces, you're not getting very much. So you're dividing by a larger number, and that's what's pulling it down to 0. If we go back up here and look at the ones we had worked on before. So for this one here, for number 11, if we think about it as the degree of the numerator, well, technically that would be 0. It would be x to the 0 power. So our degree of our numerator right here would be x to the 0. So 0 over x to the 1. So for this one, the numerator is less than the denominator. So that means for our horizontal asymptote, it's going towards y equaling 0. So we can find a horizontal asymptote as well. And for this one, here we have x and x for both. They're both a degree of 1. So for our horizontal asymptote, we would be looking at y equaling 1. Same thing for this one right here, 1 and 1. The degree of the numerator is equal to the degree of the denominator. So we would have a horizontal asymptote of y equaling 1. So here's a look at how you can solve for your horizontal and your vertical asymptotes when you are not given a graph.